Here we go. All right, so it is recording right now. I think I sent by announcement the final exam of spring semester of the spring semester, so we can look over that maybe sometime next week. Because we still have the entire next week, Monday and Wednesday, to look over that one. So this gives you some time to look at, take a look at the exam and try to, come up with the answer. And because this is a face-to-face class and we're only doing all our exams on paper, I don't mind at all if you guys want to try out, ChatGPT, just copy and paste the question and see what ChatGPT, would do with that question. So that's all fine. And we do have a fork, which is, do you want me to go over the Dijkstra's algorithm solution, or do you think, okay, we get it, it's pretty mechanical, not a problem, or do you want me to go over it? It's up to you. Okay, I see a few nods. Okay, so that does that mean you want me to go over? Okay, all right. So we can do that. And then we have a new homework assignment as promised, and it is the A star algorithm. So let me just show you the A star algorithm first, okay, as a homework assignment. And then we will go back and talk about the Dijkstra's algorithm. So the A star algorithm is due a week from today. So you have until next Wednesday to kind of finish it and turn it in. Pretty much the same setup. Okay, so if you look at it, it has about the same setup. The only difference is this time I have to give you the heuristic function. So this is the heuristic function. And then the Google Sheets is a little bit different. Okay, so if you open it up, it is, it looks a little different because, this time you have the G and the F and also the previous. And we also have A, B, C, D, E, F, G, and J. So there's one additional element. The graph is basically the same as Dijkstra's algorithm. Okay, the graphs are the same, and then you guys go like, but Tech, you did say that A star can only track one destination and one, beginning vertex. Well, that is actually true. But I have, both destinations, which are A and B from the Dijkstra's homework assignment, to transition to a actual final state J using edges of zero distances. So basically, I'm kind of like, okay, these two are both destinations. Getting to either one is fine because from either one, from A or B to get to J, would be a distance of zero. Okay, so that's basically J is kind of like a virtual destination. But you basically the bottom line is you need to get to A or B as quickly as possible using the shortest distance. The start vertex is F. Okay, so that's the other difference is with Dijkstra's algorithm, the way I present it, there's no start vertex, okay, because the algorithm finds the shortest path from every vertex to the closest destination. But A star still needs a starting point. So in this case, F is the starting point. F is the start vertex. It's all described in the homework assignment description itself here. So the start vertex is F, and the destination vertex is vertex J. And then I give you, everything that you need to know, which is the set of all the edges, the distance function, the heuristic function, and also a blank spreadsheet like this. And this one is kind of like the other one. Leave row 3 alone, okay, because it can reflect the last update on the column. Then you can stick any value, okay, in, on any row, and it will just update row 3 to the last update. So if you have a previous update here, it will only use the last update as the value shown on row 3. So that makes it a little bit easier for you guys to track what is the current value of each column. So are we okay with that? So kind of the same setup, same tool as Dijkstra's algorithm trace. And because this is your template, I'm going to have to remove all of this stuff here because otherwise you guys would all start with you some random values in the cells. So I'll be okay with how the A star algorithm homework assignment is set up. Okay, alrighty. So with that said, we'll now go back to the Dijkstra's algorithm, and then I'll go ahead and kind of show you what the solution should look like. So we go back to Dijkstra's algorithm, and the first thing we need to do is to make a copy of the template. So that's exactly what I'll do too. So file, make a copy, and I can make a copy of this in the same folder, which is shared already, so you guys can all see the solution. So I will change the name to from template to solution. And I believe you can see it right away. But I do need to get to I can't see the bottom half of the screen. Okay, let's see, does it get it done? If it doesn't get it done this way, I can do it in some other way too. Yeah, it doesn't look like it wants to get it done that way. So I'm gonna have to do it the long way. And it is, oh, there we go. All right, so I'm going to use this particular spreadsheet to solve, the question, the homework assignment. And then it is helpful to get to the description. Okay, this will work. I don't really need to look at the graphical representation. This works better for me. All right, I'm going to stick it up here so that I don't lose track of the actual graph. This is the template, which I don't need anymore. This is also the template. Which one is the copy? I think it's right here. There we go. All right, so the copy becomes the actual solution, and you have visibility of this particular spreadsheet already. So if you want to look at it from your computer, you can do so. All right. So the first thing we need to do is to do the initialization of L. And in the case of L, everything that is a destination, which are vertices A and B, would have an L value of 0. Oh, okay, I just did something that I'm not supposed to, not to change this, right? This is the first row that I can change. So 0 for both of these and infinity for the rest. Okay. I also clicked the wrong key to scroll the screen. So these are all infinity, and Q is initialized with all the destination vertices. So A and B are in Q to begin with. E prime is initialized as an empty set to begin with. So row 4 is representing all the initialization steps combined. Is that okay? Do we have any questions about that? No questions. All right. So it would be kind of helpful, if you open up the algorithm or have a paper version of the algorithm so you can refer to the algorithm as I trace it through, because I remember the algorithm already, so I don't have to go through that. All right. So the first vertex that we are choosing as V has to be a vertex in Q that has the lowest L value. In this case, the L value of A and B are the same because both of those are destinations. So that means I can choose one or the other. Doesn't really matter which one. Which one do you want me to use? A? Okay, we'll use A. So now we look into incoming edges to vertex A, which means we can just use the distance because the distance also has the same information as the edges. So we look at all the incoming edges. C goes to A, so CA is one of the incoming edges, and then GA is the other one. So GA is also an incoming edge to A, and I believe that is all. Oh, we also have B. Okay, so B is going to be here. Thank you. All right. So now for each one, I have to find out whether I have found for each of the um, origin of the incoming edges to vertex A, I have to determine, have I just found a shorter path for vertex C to go to a destination cell? So I look at L of A, which is 0, plus the distance of C to A, which is a 4. 0 plus 4 is a 4. And then I have to compare that to the length of quote unquote the shortest known path right now from vertex C to a destination cell. That turns out to be infinity. Is 4 less than infinity? Yep. Okay, so we have to update this. We have a bunch of stuff to update. And then we also have to update the solution set E prime and say that, oh, okay, by the way, we know what I think is currently the shortest path from vertex C to vertex A, and it is just that one single edge. But then we also have to add, oh, I forgot, this is classic, but I'll do this first. This would be B and C because I forgot to remove Q from I forgot to remove vertex A from set Q. So at this point, it only has B in it. So now move on to G and ask, am I finding a shorter path from vertex G to a destination cell? The answer is yes, because L of G is currently infinity, and the edge GA only has a distance of 2, and L of A is 0. 0 plus 2 is 2. 2 is less than infinity is true. So now I have to go here and update L of G to be 2. And then I have to add GA into E prime. There's nothing to remove at this point because there are no outgoing edges from vertex G in E prime yet. So there's nothing to remove. But I also have to now remember that we just changed the L value of G. So G is now on the boundary set. And last of all, we have vertex B. So vertex B has the edge between B and A has a distance of 1. So L of A is 0 plus D of BA is 1. 0 plus 1 is 1. The question is, did I find a shorter path from vertex B to a destination? The answer is no, because vertex B already has a shortest path, quote unquote, to a destination with a length of 0. Okay, so finding a path with a length of 1 is like, okay, it's not any better than the one that I have already, so there's nothing to do in this case. Is that okay? All right. So now we go back. Okay, so there's no change to Q in this case. So now we go back to the while loop, which is asking, is Q empty? No, Q is not empty. We have 3 vertices in Q. Now we have to find the one with the least L value. So L of B has a value of 0. L of C has a value of 4. L of G has a value of 2. So B is the one that we need to pick. So now we chose B, and then we remove B from the set. Once we have chosen B, we take it out of the set, and now we look at all the incoming edges to B. So we look up all the edges. Okay, so there's one coming from D. There's one coming from F, and that's it. There are 2 incoming edges to vertex B. So we focus on one at a time, and then we ask, um, did I just find a shorter path from vertex D to a destination? Vertex D currently has a quote unquote length of the shortest path being infinity. The new path that I have found is going to have a distance of L of B, which is a 0, plus the distance of D to B. The distance from D to B is 1. So 0 plus 1 is 1. Is 1 less than infinity? Okay, so we found a shorter path. We have found a shorter path from D to a destination with a length of 1. So now we have to remember to remove all the outgoing edges from D in E prime, which there's none here to begin with. But then we also have to add the new edge, which is from D to B, signifying that the edge DB is along the shortest path from vertex B to the closest destination. Okay. And then because of this, we also have to add D to the set Q. So now the set Q has C, G, and D in it. And now we move on to vertex F. So vertex F going to vertex B has a distance of 8. So, and L of B, which is the length of the shortest path from B to the closest destination, is a 0. So 8 plus 0 is just 8. L of F is infinity right now. So that means, yep, we found the shorter path. This is supposed to be 8. And we have to add that edge into E prime. So the E prime now has the additional edge from F to B. And then we also have to add F to the set Q because it is now, vertex F just had its L value updated. So we have to add it to the boundary set. All right, are we still good? Okay, so now we go back to the while loop, and the while loop says, okay, is Q empty? No, no, we just added more stuff to, the set Q. So we now look at the L values of C, okay, G, D, and F. So among these, D has the smallest L value at this point. So we choose D to quote unquote expand or explore. So once we choose that, we also have to remove it from the set Q. So Q now only has those other 3 elements. And then we look at all the incoming edges, to vertex D. So we have one coming from C, and let's see, that's it. Okay, so we only have one incoming edge to D from C. So now we ask, are we finding a shorter path for vertex C to get to the destination vertex? L of D is 1, and then the distance between CD, as an edge is 2. So 1 plus 2 is a 3. So now the question is that length of 3 shorter than the length of the currently known shortest path of vertex C to a destination? The answer is yes, because it currently the shortest known path has a length of 4, but we just discovered a new path with a length of 3, so it's time to do a bunch of updates. So this time we do have to cross out certain things because the outgoing edge from C in E prime should be crossed out now. So I'm going to cross this out. Okay, it's Alt Shift 5 to do the strike through, and then we are going to add a new edge, which is from C to D. In other words, we're telling the algorithm that CA is no longer along the shortest path from vertex C to the closest destination. CD now is along that path. Okay, so we have to make some adjustments here. We also have to add C to the set Q, but since it's already in the set, so it is as if we did not update it. But I still want to kind of copy and paste it over here to mean that, yeah, we actually did the assignment, but, because the new value is the same as its current value, it is as if we didn't do a single thing. So because C to D is the only edge or incoming edge to vertex D, so we are done for each loop. We go back to the while loop. The while loop looks at Q and asks, is it empty? Nope, it's not empty. We still have 3 more elements in that particular set. So now we focus on the L value of C, which is now 3. We just updated it. We look at the L value of G, which is 2. We look at the L value of F, which is 8. So this is the smallest. Okay, so we choose G to expand or explore next. And we look at all the incoming edges into G. So we look through all this stuff here, and it only has one incoming edge from A. Okay, so now we put the A here. Now the question is, are we finding a shorter path to from vertex A to a destination? So now, intuitively, if you remember that vertex A is a destination itself, you would intuitively go like, no, it cannot be a shorter path. But we can go through the algorithm to actually go through the calculations, because we look at the L value of G, which is 2 at this point. We look at the distance of the edge from A to G, which is 1. So 1 plus 2 is a 3. But we compare that 3 to L of A, which is a 0. 3 is less than 0 is not true. So that's how we can also come to that conclusion that we don't have to do any further steps in this for each loop. I also forgot to remove G from the set Q. So there we go. Yeah. Okay. So now when we go back to the while loop, Q only has two more elements, two more vertices in it, C and F. So C has a L value of 3, F has a L value of 8, which means, okay, let's try the C first. So now we take C out of the set. And so that means Q as a set only has F remaining. And then we look at all the incoming edges to C. So we look at everything that ends up at C. So EC is 1. Okay, so we put E over here. And that is the only one. Okay, that's the only incoming edge to vertex C. So now the question is, are we finding a shorter path from vertex E to a destination? L of C is 3. The edge from E to C has a distance of 3. So 3 plus 3 is a 6. And we compare that 6 to infinity. Then we go like, yep, we found a shorter path. So now we put a 6 over here. And then we add the new edge EC to our E prime set. Okay, EC. And then we add E to the set of Q. And then we go back to the beginning of the while loop. So now we have two more elements in the set Q, and we look at those two. L of E has a value of 6, L of F has a value of 8, so we are going to choose E to expand. We take it out of the set, so Q is now without E, and then we look at all the incoming edges of E. So the incoming edges of E is FE, that's the only one. So that's the only edge we have to consider. So, but the question is, are we finding a shorter path from vertex F to a destination? L of E is 6. So we already know there's a path from vertex E to its closest destination having a length of 6. And then the edge from F to E has a distance of 1. So 6 plus 1 is a 7. So now we compare that 7 to the path, to the length of the currently known shortest path from vertex F to a destination, which according to this is an 8. So 7 is less than 8, so we just found a shorter path again. So now we have a bunch of stuff to update. This is now 7. And then we have to remove all the outgoing edges from F in E prime. And there's only one. That should be always just up to 1. Okay, you might have 0, but at the most there should be only 1. Alt Shift 5 to strike that out. And then we add the new edge of FE into E prime. And then we want to add F to the set. But since F is already in the set, it is as if we didn't do a single thing. So now we go all the way back to the while loop again, and we ask, is Q empty? Q is not empty. It has one single element left, which means that has to be the one that I remove from the set to explore. And now we look at all the incoming edges to F, and F has no incoming edges whatsoever. So that pretty much concludes the execution of the algorithm. Do we have any questions about this? If what I just did for the past 20 minutes or so, sounded really, really boring and mechanical, well, congratulations, because you understood the algorithm. That's why it was boring to you. So are we okay with Dijkstra's algorithm? Okay, excellent. So I'm going to close this screen here. This spreadsheet, by the way, is visible to all of you. It is in the shared folder with the name of Dijkstra solution. I would add today's date to it so it's easier for you guys to find. So 2024-12-04. Okay, there we go. All right. So with that said and done, we are moving on to going back to the prologue program. So I did a little bit of work, just right before the class. Okay. So now we have, okay, so I'm going to go from the beginning, just so that we can reestablish the context. This is how I represent both the edges and also the distances, between vertices, according to the edges. So from vertex C to vertex A, that particular edge has a distance of 4, and so on and so forth. Last time we were only concerned about, can we get to a certain vertex from another vertex? So the question is, um, the question can be answered easiest when there's a direct edge between two vertices. So if the question is for variable x and variable y, can x reach y? If that is the question. If I find an edge directly between those two vertices, then we are going, okay, problem solved. Okay. The distance is completely not used. So for anything that is not used, you can always use an underscore as quote unquote the name of a variable that we are not even using. Okay, we're just going to ignore that because right now our concern is a particular vertex even just reachable from another vertex. So what if this predicate is false? In other words, I cannot find a direct edge between two vertices. Well, then I go like, okay, maybe there's an edge between the first vertex and some vertex z, and vertex z somehow is reachable to vertex y. So if that is true, then we also have found that vertex x, or I should say vertex y as a variable is reachable from vertex x. So this is how the recursion happens, which is basically implementing what we normally see as a loop. So do you guys still remember this part? Okay, excellent. So let's ignore the one with an n. Okay, so we're not going to talk about that for now. And instead, okay, I need to maximize this screen. All right, so let me see how to do that. This one, I need to, well, I suppose I can just resize it too. There we go. All right. All right, so I'm just resizing the screen. And this is, by the way, the same graph that you are using for Dijkstra's algorithm. So we can just go ahead and ask it, um, is vertex F and vertex A, are those two reachable? Okay, so we ask the question, reachable from vertex F to vertex A. Control Enter, we'll ask the question, and it just comes back and say, yep, okay, cool. And if you ask it something that is not reachable, it will come back with a false. Okay, we can, well, or does it? Okay, so we'll give it a try because it does not actually do that. It will get into an infinite loop. So we'll go back to the assignment, okay, and find me a vertex that is not reachable from another vertex. There should be plenty of examples. Hmm? G and F. Okay, so going from G ending up at F. So we just want to do the verification by hand first. So starting with vertex G, we can go to vertex A, and then from vertex A, we can go back to vertex G, and that's it. Okay, that's a tight loop thing. So that means from vertex G, there's no way we can get to vertex F. Okay, those two are not reachable. So when we go back to, oh, okay, when we go back to the Prolog, engine, and we ask the question from from what, G to F, right? Like so, and press, Control Enter. It goes like, let me think about this. Let me think about this. And let me think about this until the stack runs out of space because it's got stuck in the infinite loop. Okay, it got stuck in an infinite loop because it has no loop detection whatsoever. It doesn't keep track of what vertices it has already explored along a path. It cannot go like, oh, I'm going from vertex G to vertex A, and I'm now going from vertex A back to vertex G. Hey, that's where I started. I can just stop here. It doesn't know that. It doesn't keep track of where it has been, where it has been exploring already. So there's no loop detection in this particular mechanism. Now, of course, the proper solution is to go implement loop detection so that it knows that, okay, I started off with G and I'm currently ending up with G. That means, okay, there's no way I should explore this any further, right? So that brings us to the second version of reachable. So when you look at this reachable versus this particular reachable, the only difference is this one has got one more parameter, which is n. So n is a restriction of how many hops do I have left. In other words, if n is greater than or equal to 1, I will entertain the question of whether x and y are directly connected by an edge, because one hop is the traversal of one edge. Is that okay? And n is specifying the upper bound of how many hops I still have in order to get from x to y. So if n is greater than or equal to 1, and there is a direct edge between x and y, then I go like, okay, this is a solution. Okay, it's acceptable. Is that okay? All right. And if this fails, okay, this is how Prolog works. If there are two predicates matching the name and also matching the number of parameters, and the first one fails, then it falls over to the second one. In other words, this is kind of like a really rough way of specifying disjunction. Because if the first one fails, it goes like, wait, there's a second chance I can make it through. Let's go for the second one. So if this one fails, it is because either n is not greater than or equal to 1, which means it is 0 or negative, or I cannot find a direct edge between x and y. So in that case, I fall over to the second reachable, and then we say, okay, now this time I have to make sure that n is greater than or equal to 2, because it already failed the first time. So now I know there are at least 2 hops between x and y. So that's why n has to be greater than or equal to 2. Then I make a new quote unquote local variable. And that's how we see it from the perspective of C and C++. But in um, predicate calculus, we look at n1 as an existential quantifier. We're asking, does n1 exist such that it is n minus 1, blah, 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 so that n1, when used as the upper bound of the number of hops remaining, will help us find a path between z and y. Z is also existential, or it is quantified existentially, because we are asking, is there a vertex z such that x goes to z using a direct edge, but from z to y it is at least reachable using n1 as the upper bound. The relationship between n1 and n1 is just n minus 1. Is that okay? So with this reachable, now we can finally go like, okay, so let's try 1. Okay, can I solve this with 1 hop? No. Can I solve this with 2 hops? No. Well, okay, let's try 100 hops. No. Okay, so the upper bound cannot be more than the number of vertices, because if you want a path from a vertex to another vertex without revisiting any vertices, and you only have n vertices to begin with, that means you can only have up to n minus 1 hops in order to make the longest connection between any two vertices. Does that make sense? Okay, so that means, oh, this 100 is way more than what I need, because A, B, C, D, E, F, G is only 7 vertices. So that means, if I just bound this to 6, and if the answer is false, that means vertex G and F are not connected. There's no way for vertex G to get to vertex F. Is that okay? So this is a very tricky way to deal with the problem of having loops. Okay, because we are still wasting time. Okay, in other words, to come to this conclusion, it's going to go from G to A to G to A to G to A up to 6 hops, and then it says, oh, I don't have any hops left. Okay, and I'm still not finding F. I'm still not reaching F. So it basically gives up at that point. It's like, okay, I can't find it. Is that okay? So it is still not the most efficient way to kind of deal with loops, but it can deal with loops. Okay. Are we doing okay so far with the approach? Okay. So now I have another reachable, which introduces yet another variable here, another parameter, which is d, which is the distance or the length. So I probably should have used L for the length, but d works too. So in this case, you can see the two reachable are very much similar. Okay, this particular reachable and this particular reachable, they're very similar with only minor difference. The minor difference is here, I don't care about the distance of that edge because my only concern is, can I go from here to here? I'm not concerned about the actual length of the path. But in the second case over here, the third, actually, this is the third reachable. I actually want to know what is the length of that path. Am I concerned about the shortest path? No, but I do want to know the length of a path, if something is reachable. So the difference is over here, I say, okay, I know what the distance is, but I'm going to toss it away because it's not useful to me. Right here, I also say, hey, if there's an edge, tell me what is the distance of that edge, because I want to report that back as my own answer of in order to go from X to Y, what is the distance of that edge. So that's the only difference between um, the reachable that counts the number of hops as opposed to the reachable that also wants to know the distance of the path if the two vertices are connected. So that means I can now rerun some of the successful ones. Okay, so F to A is reachable, so we'll go give it a try. So we say F A and then up to 6 hops, and we ask, okay, what is the length of that path? Um, okay, I just press the enter key instead of control enter. There we go, control enter, and it says the length is 8. Well, does that make sense to you? Okay, let's go back and take a look at the distances or the of the edges. So I'm looking for a path from F to A. So F can go to A directly. So where is that? F, or am I? Oh, F goes to E, E goes to C, and then C goes to A, which is a 4. So that's one of the paths, right? But it's not the shortest. Um, In the solution that we just talked about, we actually know the length of the shortest path. So let me go back to the solution here. So we are now asking, what is the length of the shortest path from F all the way to um, A? Well, actually, we may not know that because the shortest path. Let's see. Let's check out what is the shortest path from F to the closest destination. Okay, because in this case, um, Dijkstra's algorithm can give us the path from F to the closest destination, which may or may not be A. So we follow these edges, FE, and then we have EC, and then we have CD, and then we have DB. So the shortest path from vertex F to the closest destination is only 7. But that's because we did not end up at vertex A, we ended up with vertex B. So from the perspective of Dijkstra's algorithm, it's good, okay? Because that's what it's supposed to find is the shortest path between a vertex and the closest destination. We don't get to choose which destination. Okay, the algorithm will automatically figure out which one is the closest destination. However, if you want to find the actual path or the length of the shortest path or the length of a path from F to A, then your choices are more limited. Okay, because in that case, you really have to end up at vertex A. And that's what the Prolog program is reporting back, is to say, yep, they're reachable, but the distance between those two is an 8. Okay, is that okay so far? But we are not interested in just the length of a path. We want the length of the shortest path. So now the question is, can we somehow make this algorithm also define the shortest path? The first thing we need to do is to find out, okay, how many hops is the minimum between two vertices? We never had that done before. So now we have a mechanism to do just that. So the whole predicate of reach does just that. So let's take a look at reach here. Um, so from your perspective, knowing C and C++ programming, you can look at n as a normal parameter. It is passed by value. And then you can look at m as a passed by reference parameter. In other words, one is telling me we are counting up to this point. Okay, that's the number of hops that we have tried up to this point. M, on the other hand, is passed by reference, which means by the time we actually find a path between X and Y, I'm going to use M to report back the actual number of hops between X and Y. So let's go ahead and give that a try. So the way you use reach instead of reachable is you tell it where you're starting, where you're ending, and also where how many hops do you want to start with, which is typically just one, and then you want to use a variable to report back the actual number of hops, which is the smallest number in this case, between F and A. So let's go ahead and press the enter key. It's only 2 hops between F and A. So now we go like, okay, are we really sure it's only 2 hops? So we have to go all the way back to the original question in Dijkstra's algorithm. So from F we can go to E, and then from E we can go to C. Okay, that's more than 2 hops already. F can go to B directly, and then B can go to A. So from F to B it is 8, and then from B to A is 1. So that would be a path with a length of 9. But that path was never documented or reported by Dijkstra's algorithm because it's not the shortest path from vertex F to the closest destination. Is that okay? Right? So now we go back to the Prolog program. Okay, Prolog, it's right here. And then we look at reach. We go like, okay, that's interesting. Because what reach is doing is it is a loop. It is counting up this time. So we are basically asking, regardless of what n, okay, regardless of what n is, let's see if we can find out whether x and y are reachable within that number. What if it fails? Well, if the first reach fails, it will go for the second reach. So when you go for the second reach, the first thing is to say, okay, let's use an existential quantifier, quote unquote, which is basically a local variable. So n1 can be seen as a local variable in typical C++ programming. And that local variable is initialized to n plus 1 because we failed with n. N is too small. Okay, that lower bound of number of hops is not enough for me to find a path. So now I go for, okay, let's bump it up by 1 and see whether it is reachable in this case. So now, using the increase n1, it will go back to this one and just try to see if it's reachable. If not, it will fail over to this one. We increase n by 1 again, and then we'll try again. Is that okay? So, but it doesn't care about the actual length, which is also important to me. So now we have reach, the second version of reach, which also keeps track of the distance. So that means in this case, I can ask the same question, but I also ask about the length of the path, between F and A, vertex F and vertex A, starting with 1 hop. And now it tells me that the number of hops is 2 and the length is 9, which is consistent with what we saw. Is that okay? But that's not the shortest path. This is not the length of the shortest path between F and A. So how can we at least know the length of the shortest path, even though we cannot spell out what the path actually has? So that becomes the next question. I ran out of time in my office when I get to this point. So what do you think? So we have some building blocks that are useful, but what I want to do is to go, okay, I need to find the length of the shortest path, even though I cannot report back what that path looks like. I want to know the length of the shortest path. So how do we go about doing that? All right, so I'll give you some ideas. So the moment we see, that in two hops, we can find a length of 9, this 9 becomes now an upper bound of the length of the shortest path. Is that okay? Because this 9, the 9 that I'm highlighting right here, is the length of a path, most likely not the shortest, but it is the length of a path from vertex F to vertex A in this case. So that means all other paths, you know, I take it back. That means the length of the shortest path is at the most 9. Does that make sense? So now I need a mechanism to go like, okay, using 9 as the upper bound, let's find all the other paths, between vertex F and vertex A. If I find a shorter one, great. Report it back as the length of the shorter path. If not, okay, 9 it is. So we need a mechanism to do that. All right. So we'll go ahead and try to construct that one. Kind of, I'm doing this impromptu, which means, I did not have the solution. I had the solution a long time ago, but I cannot remember the solution. So I'm re-deriving that solution right now. All right. So we need a mechanism to use an upper bound length of a path to limit how we can do the search. That's what we need to do. So that means we need another reachable, but this time it is length delimited and not hops delimited. So this time I'm gonna I have to use a different name because otherwise it's not gonna work. So I have to use a different name, which is um, length limited reachable. Okay, there we go. Length limited reachable from X to Y. And this time I have to specify how much length is remaining for me to find that path. So, this L is going to be the upper, okay, we'll use U as an upper bound and then use L to report back what is the actual length that we have found up to this point. Okay, so we'll go like, okay, the construct or the um, logic of this reachable is similar to the previous reachable, which is this one over here. But instead of using the number of hops as a limit, we're using the upper bound as a limit here. So now we can say the upper bound limit has to be greater than or equal to, well, let me see. It's going to be a 0. The question is, do I want it to be greater than 0? Do I want it to be greater than or equal to 0? We'll try greater than or equal to first. Okay, so that means I might still be able to find a path between x and y and meeting the upper bound limit. So once this requirement is satisfied, then I would go ahead and use the same approach here, which is the ground case. This is the non-recursive case, which means if I can solve this with a single edge, we are good. So now we say, okay, give me an edge, confirm that there's an edge from x to y with a distance of d over here. But now I also need to make sure that d is less than the upper bound. Okay, so we need to double check that. So we want d to be less than or equal to, or I can say the upper bound is greater than or equal to, this time for sure, the distance between x and y as an edge. If everything works out, then we can say L, which is the length of the path between x and y, is just that d, and that concludes the base case. Okay. So what if this fails? What if I cannot find an edge? Oops. So what if I cannot find an edge between x and y, and I still have some upper bound left? Okay, so that will fall to the second, length limited reachable. So now I have another length limited reachable here. reachable, x, y, upper bound, and length again. So remember L, you can imagine L as a pass by reference parameter. I'm only using it to pass back a value of the actual length of a path. U is passed by value. I'm using it to specify an upper bound. It's like do not exceed this much. So so if the first length limited reachable fails, then the second one is going to look like this. Okay, we still need the upper bound to be non-negative. And this time I'm looking for an edge between x and some vertex z with a distance of say d1. And then we can now say you can put in this first, okay? Because if u is still greater than or equal to d1, then we are still good, okay? We still have some remaining upper bound for the remaining path. So now we can look for LL reachable um, between z and y. And I cannot remember whether I can do that. So I'm just going to use another existential variable, which is basically the same as a local variable. So this is going to be u1, which is the new upper bound. The new upper bound is the old upper bound minus d1, because d1 is the length of the edge that we have found here. So the new upper bound is going to be the upper bound minus d1. And now I use the new upper bound for this recursive call. But whenever it reports back as L, we are going to use L1 to represent it. And then if all is good, then we say L, which is my answer, to my caller is just L1. So therefore, we are now relating the recursive call answer to my answer back to whoever called me in the first place. All right, so let's give it a try. So we have LL reachable. And this time, I'm just going to give it the example from before. I want to go from vertex F to vertex A. The upper bound is 9. And I want to find out whether there are paths, what is the length of the shortest path with 9 as the upper bound. Okay, Control Enter. It is 4. So now the question is it really 4? To go from vertex F to vertex A, the length of well, I mean, the length of a path, okay, another path is 4. So the question is that the case? No? Okay, we'll find out. I think I forgot to add. Yep, I forgot to add because L is what I need to report back is this L1 plus D1. I forgot about that. Okay, let's try again then. Okay, it is 8. Okay, I think 8 is the correct answer. But is that the correct answer? In other words, is that really the minimum of all the alternative paths? We don't know for sure. Okay, we know it is shorter. Okay, it meets all the criteria, but is it actually the shortest path? That we don't know yet. So that means, okay, we need something else to address the problem of are we finding the shortest path, or is it just the length of a path, but not necessarily the shortest one? So how do we do that? Okay, so that's okay from the interactive side, but it is not programmatic. But it's a good experiment, right? So we can try that. It says false. Okay, well, not too bad. Or we can just make it 8, and it is just reporting the same thing as 8. So now what I'm going to do is to say, okay, the upper bound is exclusive, which means it has to be less than the upper bound. So in order to specify that, we have to make this reachable to be, it has to be strictly greater than 0 in this case. And this has to be strictly greater than D. This also has to be strict here and strict here. So this time, reachable, LL reachable means the upper bound is exclusive. Okay, I can find a path of a length that is up to but excluding the upper bound itself. So with that modification, this becomes false. Too many open queries. Okay, stop. Stop. Okay, let's try again. It becomes false because 8 is the actual length of the shortest path. There are no paths with a length shorter than 8. Okay, so now that's kind of useful, but we have to do this manually, right? Because we started off with, oh, okay, we found a path with 2 hops to get to a path with a length of 9, which means 9 is quote unquote the upper bound. And then when we plug in upper bound 9, we found a path with a length of 8. And then when we plug in 8 as the upper bound, we go like, oh, okay, there are no paths with a length of less than 8. So now we know that the length of 8 is actually the shortest. Okay, so how do we codify that? How do we code it in Prolog? Okay, so let's give it a try. Okay, so we'll construct the query as we go. So we basically let's say length of the shortest path, okay, between vertex x and vertex y, and we'll start with that. Okay, all right. So the very first thing we need to do is define an upper bound. It's like, okay, just find me a path and use whatever length that thing has as the upper bound. So that is done by just reach. Okay, so we say reach. We need to reach from x to y using 1 hop as the beginning, and we can go for any number of hops, but tell me how long it is going to be. So the m we are not even going to use, because it's not really useful from the perspective of this thing. So now that we have the upper bound, which is this L here, then we can say, okay, give me paths that are, give me another path using L as an upper bound. Okay, and I need to report back that L2, so I need to go, report this L, but this is gonna be L1. We don't know whether L1 is actually L. Okay, L1 is the upper bound. L is the actual answer that I need to report back. All right, so L1 is a good upper bound. And now with the upper bound, I can use LL reachable. So now we say LL reachable from vertex x to y. So xy is still the same, but now I'm using L1 as the upper bound. And I need to know, using L1 as the upper bound, do I get an L2 back? Because the only way this will come back as true is L2 is less than L1. So now we go for the next one. Hmm. Because what we need is, um, okay, I know we have to negate something because we have to be able to say there are no shorter paths. So I think the way I structure LL reachable may not be the correct one. Let me think. Nope, this is okay. I think this is okay. All right. So before I implement the next step, let me just do something like this. Okay, so I'm just going to go back to reach instead of LL reachable. So we'll just go back to reach from F to A, starting with 1 hop. Doesn't matter where we end, and it doesn't matter how long the path is. I just need to know how many hops and what is the length of that path. And then I press Control Alt here. And do you see how there's a next here? That means there may be other solutions. Aha. And then we have all of these alternative solutions, But you can see the number, it goes from 9 to 8, back to 9, back to 8, back to 9, because I think there's a path here that has a zero cost edge, and that's why it's alternating between these two. Okay, so now we're starting to get even longer ones. So that means reach is not only going to report back the length of one path and also just one hop number. It will go for all the possible ones, including the ones that are going through loops, which we don't really necessarily need to deal with. So what that means is it is possible to explore multiple solutions. So now we can say so we basically keep this one here, and then we say L is L1. But we also want to go back and say we cannot find a shorter path. Using L1 as the upper bound, we cannot find a shorter path. So that means this L2 is not really used in any way. We are only, um, it just needs a place here, but we don't really care about it. All right, so it complains about singleton variables L, M, and L2. So let's see, L is L1, but L is what is being reported back. So I think we need that. L2 is here, so we can just replace it with an underscore. I think this is it. Okay, we'll give it a try. LSP, length of shortest path from vertex A to vertex F to vertex A, and we want to know the actual length. Okay, Control Enter. It is 8. Seems right. What about FB? What is the shortest path from vertex F to vertex B? We just solved it earlier in Dijkstra's algorithm. 7. That is correct. So we'll give it a try, and it finds it. So this is the trick, which is this particular predicate will kind of go back and give us alternative solutions. It will keep trying, okay? And this one is saying, okay, can we find a shorter path using L1 as the upper bound? Is there a path that is even shorter? So we are basically going like, okay, I just found a path with a length of L1, okay, and I potentially want to report it back and say this is my answer. But we are also saying that and not we have a shorter path. Because if this is true, if the not finding a shorter path is true, then the whole thing is done. But if this is false, that means it has to go back and say, okay, let me find you another path where there's no shorter path, you know, in existence. So this is why this LSP is working, and M is not used simply because it's just counting the number of hops to begin with. So that means I can also replace it with a underscore, and that will get rid of the singleton variable error message. It's just a warning in this case. It's not necessarily an error. Too many, because all of these have alternatives. So there we go. So now it works without a problem. So what do you think? Yep. Hmm? Oh, why is it saying there's an alternative? Because they're all just 7. It goes back and re-explore the same path basically. All right. So that's kind of how we. Oh, look at that. It's cute. There's a little RIP, rest in peace symbol because I aborted the whole thing. All right. So I just derived the solution or the algorithm, step by step, not out of memory, but just out of reasoning. It's like, okay, I think I need this, and then did this, and so on. Um, so what do you think about the style of programming in Prolog? I can see people turning their head this night. No, this is not the way I want to do my own programming. If you think this is bad, Lisp is actually worse in many many ways. LISP stands for list processing. If anyone, I'm not sure whether that is still true. If you're transferring to UC Berkeley, UC Berkeley used to teach Lisp or a dialect of Lisp, which is called scheme as their CISP 300 class. So instead of using Python or in pseudocode, they use Scheme, which is a dialect, which is a sub language of Lisp, as their first programming class. I'm not sure whether that's true. Do you know that is still true? Uh, nah. So you can look it up, Berkeley Scheme Introduction to, I guess, programming or computer science. Yep, there we go. Simply Scheme Part 1 Introduction. And the scheme is actually easy compared to actual Lisp because actual Lisp is, I don't even remember the term to do that. It has to do with Lambda. It is Lambda complete, I think. I can look it up. But anyway, in terms of programming concepts, Scheme is also considered a little bit easier compared to Common Lisp because Common Lisp is the whole environment is carried around when you are in the flow of the program. There's no such, it's just a whole lot more difficult to deal with. There are fun concepts in Common Lisp. All right, so that's pretty much the demonstration of Prolog, but that's not the theoretical part of predicate calculus. This is actually how we apply it. So if we go back to the actual translation of LSP in this case, the question is, what does that actually mean? Okay, so I'm going to use comments here so that I can actually just talk about what that means. So in terms of the meaning, if you remember from the previous lecture, the colon dash symbol means implied by, okay, which means it's the opposite direction of how we usually spell out implication. So in this case, it means every every variable that is named in the original predicate, they are universally quantified. So that means in this case, it means for all x, y, and l in parentheses. Okay, so now we have to specify what is the actual statement being made. So the actual statement being made, first of all, we have to identify the variables that are used inside the sentence, but not as a part of the parameters. So in this case, we only have L1. So now L1 is an existentially quantified variable. We say there exists L1 such that. So now we are down to the actual Boolean expression. So the Boolean expression is basically saying, I'm going to translate everything into just English, sentences. So the first one is x, y is reachable from x with a length of L1. Okay, so we'll just spell that out. Okay, there is a path of length L1 from x to y. The comma here is a conjunction. So that means, over here, we just have to say and, okay, L is L1, okay, fine, the L is L1, and then we have one more and. That one is the crucial part because the backslash plus is a negation. So we are basically saying it is not the case of what? LL reachable XY L1, whatever the underscore is saying um, um, there's no path from X to Y with a length of less than L1. Okay, let me put this on the next line here. So that's basically what line 67 to line 70 is really saying. Yes. Oh, that is correct. Not path from XY with a length of less than L1. You're correct. But that's how you read Prolog programs and translate it back into quantified expression. The whole point of predicate calculus is the statements are quantified because in propositional calculus there's no quantification. There exists, there's no for all, and so on. And predicate calculus, which is also known as second order logic, allows you to specify quantifiers. And and it does make sense, okay? Because if L is the shortest path between between X and Y, then the quantified expression here actually makes sense. It's not the shortest way to describe it, but it does make sense because L is the length of a path from X to Y, and there are no shorter paths from X to Y. So that makes L the length of the shortest path. Okay, it's just that the way you specify the logic and the flow of the logic is a little bit kind of on the awkward side, and the syntax is also definitely on the awkward side too. All right. Any questions about predicate calculus? So I just related predicate calculus to the graph thing because I used it to find the length of the shortest path. I don't want to show the code to find the actual shortest path because I have to introduce the concept of a list, in order to keep track of the actual path itself. So this one only finds the length of the shortest path, but it doesn't really show you what the shortest path looks like. All right. So let's go back all the way to why are we even interested in propositional calculus and predicate calculus? What are these things intended for? We'll start with propositional calculus. Who invented propositional calculus? Is it Alan Turing? Is it Dijkstra, who is one of the greatest modern day computer scientists? Is it Knuth, who is still alive and he's still teaching some classes at Stanford? Who invented propositional calculus? A way long, long time ago. I think it's some Greek, right? So that's not computers did not even exist. So what is the purpose of propositional calculus? It cannot be because of computer science. Okay, if there are no answers here, I'm gonna ask ChatGPT. I will do the same thing as most people do. What is the purpose of propositional calculus? Okay, so I will give you my answer first, and then we'll see whether the answer matches what ChatGPT has to say. It was a formalization of arguments. Okay, so when people say, okay, um, they just present a bunch of propositions, which are statements. Okay, the statements are not necessarily saying what is true and what is not true, but it's about expressions being true or not. So they can say A implies B is true. But is A true? Is B true? No, I don't know. I just know the implication itself is true. Okay. Or they can say something like A or B or C is true. You go like, but there are many ways to make that disjunction true because we only need at least one of them to be true. So that means A can be true, the other two are false. B is true, the other two are false. C is true, the other two are false. A and B are both true, C is false, and so on, right? There are many, many ways to make that particular disjunction true. So when you have a whole bunch of those declarations, okay, you say A implies B is true, but we don't know whether A itself is true or not, B is true itself is true or not. We say A or B or C is also true. You don't know which one is true. We want to find out another expression, whether another expression is implied to be true because of all of these declarations. That was the purpose of propositional logic, okay, or calculus. So we'll ask, ChatGPT. Okay, it's also known as propositional logic or centennial, sentence related to sentence, I suppose. Logic serve as a foundation branch of logic that focuses on the understanding and analyzing the relationship between propositions, statements, and the truth value. Blah 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 blah. Okay, there we go. It gives you a really long explanation. It's a tool to study for studying how truth flows through logical structures, serving as a foundation for reasoning, problem solving, and formal systems in mathematics, philosophy, and computer science. Now, computer science did not even exist, okay, when propositional logic came around. You can also ask, who came up with it, right? Who came up with proposition proposition logic or calculus? Calculus, question mark. All I need to see is BC, a long time ago. So now you go like, okay, so why do we study propositional logic in a computer science class? What do you think? Because I don't want to just give you a bunch of mechanical stuff and go like, okay, now I know the mechanical stuff. I don't know what it is about, but I'm getting through this class. I'm done. So what is the purpose though? Why is it in the curriculum today? Yep, yep. But that's predicate calculus, which is related, but but yes, I just showed you the code. So what was the purpose of Prolog? When people invented Prolog as a programming language, did they invent it because I just want to punish myself with a programming language that is really, really hard to translate into iterative logic that you are all used to in C++ programming? Or did it serve a particular purpose? Okay, so we can ask that question too. Okay, so what was the purpose of the invention of Prolog, the programming language? So I can count on ChatGPT to be for its knowledge, right? So the knowledge part, I can trust it. So automated logical reasoning was one of the main reasons. AI, this is back in the 90s or the late 80s and the early 90s. That's considered AI at that time. Facilitating natural language processing. And so these are all kind of interesting because these days we use neural nets to solve every problem, which is the polar opposite of propositional logic or Prolog, because that is completely pure symbolic processing. You give the program the same prompt, you ask the same question, it always gives you exactly the same answer. You can ask ChatGPT the same, you give it the same prompt twice, it won't give you the same answer. Okay, there'll be a little bit of difference between the two answers because there are always probabilistic stuff going on with the neural net when it's quote unquote random walking. That's my term for what it does. Um, okay, but relating back to modern day computer science, what do you think is the greatest? If you have to pick an occupation, let's just say that you are qualified for that occupation related to computer science. Which one has the most job security? I'll give you two choices here: game developer versus cybersecurity computer scientist. People always need to play a good video game. I'm going to pick game developer. Nope, and at any economical downturn, people are going to try to save the money and go like, do I want to upgrade to the next version of this game, or do I want to buy the skins of this game? No. Okay, so all the game companies, their profit margins just goes way down. Is that going to deter other countries from trying to hack into the systems of the United States? Nope. So computer security scientists, okay, will always have their jobs. But what does Prolog, predicate calculus, propositional calculus have anything to do with computer security? That's the link that I'm asking you guys to make. Okay, so let's just say that you're writing a program for CISP 430 because many of you are taking CISP 430. How do you know your program is right? Hmm? I don't want to hear that. Okay, so you said using cout statements, you're tracking, and you have to give it test cases, right? So most people just say, okay, I know what this program is supposed to do, so I'm going to throw some test cases at it, and I know for these specific test cases what the correct answer should be. So that's how most people, test their programs. But how do you know that there may be a flaw in your program where your test cases just did not exercise those branches and cause the problem to show up. You can never know for sure, okay, especially for complicated programs like an operating system or a TCP/IP stack, within an operating system. But those are very related to computer security. If your mobile phone app that helps you, navigate to a certain location is not working, I mean, I know there are fatal cases. I think the news just reported, 3 people died because the app led them on a bridge that was only half finished. So the car just kind of drove all the end to the end of the half finished bridge and it fell. The car fell, and then everybody died in the car. Yes, so there are those situations. But if your TCP/IP stack or if your SSL library has a flaw, then the consequence is a lot worse than a few people dying. I'm not saying a few people dying is not good, it's not bad, it is bad, but having a security flaw like that is even worse. So I think I pointed out about this before. It is called the hard bleed um, vulnerability. Okay, so if you go to the hard bleed bug, you can read about it. Okay, it is about a library that deals with SSL, TSL, encryption. It has a flaw. The flaw does not stop it from working when the packets and the protocol is followed. It is only going to reveal memory content when you present to it a malformed packet intentionally. So that means if everybody is playing by the rules, that bug is not going to show up. It's not a problem. But what do hackers do? They try things outside of what is supposed to be done. So that means, so how do we stop something like this from happening? It would be nice if we can just, present the RFC of a certain protocol or encryption algorithm or whatever and say, this piece of code is supposed to do just that, no more and no less. And you have a mathematical proof to say, yes, it is conclusive. Okay, I mathematically prove that this piece of code would only do what is specified here. That is the reason why practical calculus, propositional calculus, and theorem proving in general to be of high value in computer security. Now, how far have we gone? I have not I have not tracked the progress, currently, but I know that it's not fully done yet. Okay, and the current approach of AI, of using neural net to do everything, I don't think it's the right solution because it's not deterministic. It is kind of probabilistic in many ways. You can still do things to make it super helpful and super useful, but proving theorems in a conclusive and deterministic way is still not there yet. Okay, and ideally speaking, we want to prove the entire operating system is correct. There's no flaw in the entire operating system. Don't you think Microsoft would be interested in that? Yep, but it's not done yet. So that means there's still a lot of work in this particular direction. That is kind of what I want to say because I want to connect what we learn in this class to potential employment opportunities that I know is important. Um, just to close the class, I know we are 5 minutes over already. Did you guys read news that the US government, multiple branches of the US government, is now warning the general public of do not send text without encryption? No? Okay. I will show this as the last piece of today's class. Okay. US government warns um, SMS as text getting hacked. There you go. Forbes magazine, FBI, along with multiple other branches of the federal government, warns your iPhone and Android users stop sending text unless you know that it is going through end to end encryption. And you can read the rest, okay? I'm not going to read the rest of this article, but you can read the rest. So that means computer security, generally speaking, is a big topic because there are organizations and entire countries, big entire countries, who want to hack into everything. So you have an active adversary. You're not basically competing with another gaming company or game development company. This is active. People are actively trying to get into the system, which means you also need to actively stop people from hacking into the system. So that's kind of important when you try to plan, what your career options are. All right, that's all I have to say. I promise this is it. I will see you guys next Monday. Don't forget the homework assignment.